Hello, welcome to today's COSI seminar. We have Professor Amit Ashok from the University of Arizona here today as our guest speaker. He's an assistant professor in the College of Optical Sciences and in the Department of Electrical and Computer Engineering. He received his master's degree in electrical engineering from the University of Cape Town in South Africa and his PhD from the University of Arizona. He worked at Omnivision CDM, and then he moved back to Arizona, where he now directs the Intelligent Imaging and Sensing Lab, which focuses in the area of computational imaging, statistical interference, and intelligent system design. So, welcome.
Thank you, Ariel, for that introduction. So I just wanted to thank for the invitation to come here and talk about my research work. It's a privilege. In some sense, I consider this at least to be the birthplace of computational imaging, at least in its modern reincarnation. And I think we have the honor of having one of the pioneers at DOSKI here. So thanks again for the opportunity. As you can tell, I'll be talking about computational imaging, but with a slightly different spin, so to speak. What I'll focus on is how we can leverage the paradigm of computational imaging to do task-specific, basically, approach to imaging. And that will become clear as I start to motivate the talk. So this is a brief outline of the talk. First, we'll start with kind of the question, and it might look silly to ask, but why do we make measurements? And that's kind of the motivation for task-specific approach. And then I'll talk about how computational imaging is kind of ideal for doing that kind of task-specific imaging. Later on, I'll talk about some example cases where we can use the task-specific approach. One broad class of applications is using optical point spread function engineering, of which extended depth of field is a special case. So in fact, I'll talk about some of the work we have done recently along those lines as well. And then I'll talk about the other dominant application that we deal with in our lab is compressive optical imaging, which I think is as a special case of computational imaging because computation is an inherent part of the image formation process. And then I'll end with some concluding remarks. So to start with this question, why do we make measurements? Well, I mean, as most of you know, traditional sensors are designed with the goal of capturing some physically observable variable, right? For example, electromagnetic field, invisible light, infrared, in all spectrums. It could be temperature, mass, pressure, or spectrum, right? So traditional sensors or imager capture that directly. Now, why do we do that? Kind of the why behind measurement varies, depends on what you want to do with the measurement. Well, the most kind of common case is basically art or aesthetics. You want to capture a moment, say with an optical camera, right? I mean, that's kind of the main motivation for design of optical imagers in the first place. So we want to capture the moment as we see it. That's the goal, right? So you want the image to be as high quality in terms of it being a faithful reproduction of the scene. So that's one use case. Now in some scientific applications, we might want to understand some new physical phenomena or mechanism. So by observing multiple physical variables, we can learn or further our understanding of that phenomena. Or many cases in scientific application, you might want to test a hypothesis that you have about a physical phenomena. In that case, the answer you care about is whether you want to accept or reject that hypothesis. So yes or no. In yet other applications, we want to quantify physical variable variation, say temperature versus time or something like that. Then moving across, into kind of different segment of applications, say in defense and security, in many cases, we want to tell if there's something dangerous present in the scene of interest. So for example, when you go through the airport, the X-ray scanner, the only thing you really care about if there's an explosive or a high-risk item present there. You don't necessarily care what the bag looks like necessarily, at least not directly. So in those cases, you have a very specific task in mind that you want to basically answer that question. Same thing in surveillance. Once you find something of interest, you might want to track it. And in that kind of application, what is in the background is not really of importance. All you want to know is the trajectory of the target to as much precision as possible. And again, in other applications like security, you might want to do verify identity. For example, in a fingerprint scanner, you just want to know whether the person you're claiming that you are, is that correct or not. So in some sense, the goal is just a yes or no answer, right? Whether it's validated or not. And so on. I mean, there are other applications. So the why behind the measurement is kind of important. And sometimes we seem to kind of ignore that and just capture the signal and then worry about why later. And that has certain costs. So once we get a measurement, how do we quantify system performance? In many cases, if not all cases, if you are trying to faithfully reproduce a signal, then mean square error is a typical metric used, especially in optical imaging. It determines the fidelity of the optical imaging system. But the fidelity is an indirect kind of criteria. It depends on what you want to do with that image, right? So for example, one of the problems with MSE is that for the same MSE, you can have different kind of distortions in the image, and this is probably very well known in image processing at least, and it gives you the same kind of MSE, right? But depending on what you want to do with the image, it might have very different consequences. If you want to do detection, or if you want to do quantification, these distortions are specific to that task, right? So basically, the task performance may not be monotonic in MSE. So if you make the MSE smaller, higher fidelity, your task fidelity may not improve with that. So an example of that, I don't know how clearly visible that is, but these are like a set of images. The left-hand side has larger distortion as measured in MSE, and the right side has lower distortion. But the probability of detecting, say, this target in the background is actually higher in this case than in this case, which is counterintuitive, right? And the reason that that's why the case is because in the right-hand side image, where the MSE is larger, basically we have designed the optical system so that some spatial frequencies have higher weights, which carry more discrimination information as opposed to other frequencies. So when you do that, you may end up increasing MSE, but from the detection point of view, where the discrimination information lies, you actually enhance that. So you get larger probability of detection. So basically, the kind of point of this is that we want to employ task-specific metrics when we design and analyze imaging systems or even computational imaging systems in general, right? So we want to match what we are acquiring to what we want to answer at the end of the day. And in some sense, computational imaging is an ideal kind of paradigm for doing that. So typically in this kind of talk, I spend some time motivating computational imaging, but here I don't have to do that. I can get right into the kind of meat of the talk. But as you know, in a computational imaging system, there are kind of three key components. You have the optical encoding, you have the sensor, which may be a smart sensor. It can do kind of inherent processing, and then you have post-processing, which is kind of key part of computational imaging. That's the computation part of it, right? And as a result of this, you end up with some image or data. And for example, if you're doing target detection, all you might get is a yes or no answer, right? So this is where we can inject this task specificity of the application into the design of the system, right? So we can close the loop, and we can design the system to maximize the performance for a specific task instead of just maximizing the fidelity, say, in MSE, right? And so what is the cost of doing it in the MSE way? Well, we might be spending both system resources and photon budget in acquiring information, or I should say data, which is not relevant to the task, right? So it's inefficient from that point of view. So if we know the task ahead of time, we know what we want to do with the data, then we can be smarter about that design. So we take the available photon budget and maximize the information extraction from that process. So basically, yeah, we want to quantify and optimize imaging system performance using task-specific metrics. Some examples of those are MSE. For example, if you're just doing visual fidelity, MSE is not the best metric, but it's one of the metrics. If you're doing target classification, probability of error could be another metric. For detection, you can do probability of detection for a fixed probability of false alarm rate. Other metrics is area under the curve, under the ROC curve, or this kind of information-theoretic metric of task-specific information, which I'll talk about later. So this is a fundamental measure of information which is kind of tailored towards the task you want to do, and in some sense, it encompasses any other metric that you might want to use. So within this kind of framework of computational imaging, using a task-specific metric to close the loop of the design, I wanted to share with you some of the example cases where I've basically applied that. So the first broad kind of class of systems that we have applied this idea to is basically optical PSF engineering. So as I mentioned before, EDOF, or extended depth of field, is an example of that, where you change the optical point spread function of the system, in conjugate with some specific processing to achieve your design goal. So for this particular application, we are interested in digital super resolution. And what digital super resolution means as opposed to optical super resolution is in many imagers, you are actually resolution limited by the pixel size. It's larger than the optical size. So if we want to resolve, say, 2 points in the object, they are resolved optically, but because of the large extent of the detector, we lose that resolution, right? So that's what I mean by digital super resolution. How can we overcome this detector limited resolution? And there are kind of two degradations which are happening in the detector. One occurs from the spatial integration from the large extent of the detector. So that causes blurring. And the second part is the large pitch, which is the undersampling. So you get aliasing, right? So as a result of those two phenomena, you get degradation of the object, or sorry, image quality. So in this particular case, the optical resolution is 0.5 micrometers, but with about, let's see, I think 15x undersampling with a 7.5 micron detector, this is the kind of image you end up with. Now, of course, you can say you can interpolate, but interpolation is not going to give you, at least linear interpolation is not going to retrieve that information for you. So the traditional kind of technique, if I can call it that, for solving this problem is something known as multi-frame imaging or subpixel shifting. So the underlying idea in that is that if you have one measurement where a detector is larger than the optical spot, so for example, these 2 points are not resolved, you can shift your focal plane array by subpixel shift and arrange it such that these two spots align onto two different detectors. So now you've resolved that, right? And as I collect many such measurements which are subpixel shifted, in theory, I can recover the optical, the resolution of the optics depending on the number of frames that I'm going to use. So basically, the reconstruction part is just generalized sampling theorem by Populus that we use here. So nothing magical there. But in theory, you need all the number of undersampled frames to recover the full resolution. So if I had basically f amount of undersampling in each direction, I need f square number of these subpixel shifted frames to recover that. So these are some examples of that, simulation examples. If I do 4 subpixel shifts, I can improve the image quality like so. And going up to 10 by 10, you can see we have almost recovered all of the resolution, not quite all, but majority of that, right? So one thing to notice in this kind of application or solution is that all we are doing is basically exploiting the subpixel shift. We are not changing the optics at all, right? So that's an additional degree of freedom that we can exploit within the computational imaging framework. And the basic idea there is that we modify the optical point spread function so we get a larger PSF, basically larger extent. And you can imagine by basically, in essence, by calculating its centroid, you can get subpixel resolution, right? At least for kind of sparse arrays in the scene volume. So that's the basic idea. We have to spread the PSF. Now, of course, when we do that, we have to make sure that we are not losing the optical resolution. So this comes at the cost of basically loss of MTF, right? So it's a trade-off. We lose some MTF, but we are able to get this subpixel resolution. And then we combine it with this more traditional approach I talked to in the last slide with subpixel shifting. So now I'm going to engineer the optical PSF in conjugate with shifting the array. And basically, you could implement it like a multi-aperture system. So you can have 4 apertures, for example. Here, I have 2 by 2 number of frames, and in each aperture, the optics is modified by basically placing this phase mask. And in this particular case, actually, we used a random, pseudo-random phase mask that we designed its roughness and correlation, basically length, to maximize the imaging performance. Now, in this particular case, since we are interested in the fidelity of the imaging system, we used resolution as the metric to optimize the system. So that's the task-specific part of it. So when you go through this optimization, we can basically compute the performance of the optical point spread functioning approach versus what I call the lens approach. So in the lens approach, we don't change the optical PSF, we are just doing subpixel shifting. And in this purple approach with the random phase mask, we are doing basically combination of both. And this plot basically shows the angular resolution of the resulting computational system versus the number of frames I'm collecting, right? So in this particular case, the undersampling was 4 in each direction. So by the time I collect 16 frames, I can fully recover the optical resolution, right? Now, of course, there is a slight gap you can see between the curves here, and that is a result of non-zero noise in the system. So you're noise limited in that sense. But the key thing to observe here is that this is the lens approach. You can see the angular resolution is improving quickly, but with this purple or point spread function engineering approach, we can basically get much better resolution as measured by the resolution metric with the point spread function engineering. So these are some reconstructions based on that approach. So you can see in the purple or the point spread function engineering approach, even with one frame with no subpixel shifting, just by the virtue of optical PSF engineering, we can recover a better quality of the image, right? And so the reason why this works is, in some sense, we are exploiting the smoothness of images to be able to kind of deconvolve that, right? So because of the smoothness of the image, even in one sample, right, we can get pretty close to the diffraction limited resolution, not all the way there, but quite close to that. And the extent of this is, of course, limited by noise. So as your noise goes up in the system, your resolution gain is going to fall accordingly.
So
yes?
When you increase the number of frames, actually you are increasing the resolution of the stage moving to the detector, right?
Yes, so you have to get finer subpixel shifts.
Yeah. The reason I see the diffraction limited resolution is because that resolution has exceeded your optical resolution.
The diffraction limited resolution is the optical resolution, right? So that is not changing as I get more frames.
The shifting resolution is exceeding that optical resolution, so the final resolution is higher than the diffraction limited resolution.
No, so this is the optical resolution limit, right, that we can never overcome, at least in this application. So we are not doing optical super resolution. All I'm doing is recovering most of the optical resolution, right? Because my detector is degrading the resolution, which the lens has already formed. So the subpixel shift I'm doing is is comparable to the optical resolution. So you have to be able to control that accurately, right? Whereas with just one frame, you don't have to do any shifting. So this one doesn't involve any shifting. This is purely point spread function engineering, right? So in the spirit of the task-specific kind of approach of this design method, we can apply the same PSF engineering basically with the same problem where your detector resolution limited, but to a different problem. In this instance, iris recognition, right? So it's a different task. The goal is not to necessarily produce a pretty picture. The goal is to be able to verify the claim of a person that this iris belongs to them with as high an accuracy as possible. So traditionally, how the systems work is that, in this particular case, of course, you're pixel limited, but if you're not pixel limited, you have the high resolution image of the iris, then you segment this kind of iris part of it from the sclera, and then basically you have to do some post-processing. In this case, we apply some wavelet filters. So you take the segmented part, you unwrap it, make it into a rectangular part, you apply wavelets, and you apply some thresholding, and basically you end up with this kind of iris codes, which are binary codes. So this you can think of as a barcode of an eye, right? So when you have pixel limited resolution, of course, it degrades the image quality, but in terms of the iris pattern, right, or the code pattern, it also degrades that. So when we try to match, say, this eye with this measurement, and this code is in my library, and I try to do a match, say, with Hamming distance, right, you will get errors because this code is now degraded as a result of your limited resolution. So the goal here is to maximize the detection performance, not necessarily the resolution, right? Of course, you might imagine that if I improve the resolution, detection performance improves, but that improvement may not be linear or even monotonic necessarily. So in this case, we will quantify the imaging system performance with a statistical error metric. So as many of you might know, if you have a detection problem, you have basically two kind of errors which can happen, right? You can have the false alarm rate, which is basically detecting a person when they're not claiming to, they're not who they're claiming to be, so that's false alarm. And you can falsely reject a person who is indeed the right person, but your detection algorithm failed, right? So you have these two kind of errors that you can make in a detection system. Now, of course, you cannot simultaneously minimize both errors at the same time. So you have to pick one and then maximize the probability of detection. So in this particular case, we were considering search applications. So what we did was we fixed the false alarm rate to 1 in 1,000, and basically then tried to maximize the probability of correct detection of the iris, right? And basically from statistical signal processing, you may know that's basically the Neyman Pearson criteria, right, for optimizing a system. So that was the metric in this case, and we applied a similar approach like in the last PSF engineering case. We had multiple subpixel shifted frames, and in this case, we actually parameterized the phase mask with Zernike polynomials. So I think this particular example, we had 24 coefficients that we could optimize. So we have 24 degrees of freedom in the optics, and then we had a couple of degrees of freedom in the algorithm, and we jointly optimized the algorithm and the optics to maximize the probability of detection, right? So it's not directly maximizing the resolution. So when you do that, we kind of end up with this kind of phase mask. Now, of course, this depends on the SNR. So I think this particular case, our SNR was 30 dB. If you have a different SNR, your phase mask design would change. So that's the optimized phase mask, and this is the corresponding point spread function. You can see it has extended structure. So in some sense, it is using the similar idea like the previous example, but here the goal is not necessarily resolution enhancement, but improving the detection performance. And just for comparison, that's the diffraction limited PSF. So just going back and forth between the two, you can see the larger extent of the PSF is clear. So here are some performance comparisons as a result of this design. So what I have here is we fixed the false alarm rate, as I mentioned before, to 1 in 1,000, and then we are trying to maximize the probability of correct detection. So the conventional system where you have no undersampling, you're optical resolution limited. With the kind of data sets we had this kind of error, which is not great, but then again, our image processing technique wasn't probably the most sophisticated version that you have available. But as you can see, when we have undersampling of 8 by 8, so 8x in each direction, you have 8x undersampling in each direction, and if you say only acquire one frame, the false rejection rate, in this case, reduces to 0.458, which is close to 0.5, right? So the system is pretty useless, right? You can just flip a coin, and the resolution or the aliasing has completely destroyed the system performance. Now we can do the, so sorry, this is the length shifting part, right? So there's no subpixel shifting when you have only one frame. When you do 4 frames, you start to recover that performance. When you get down to 16 frames, you have almost recovered all of the performance as the conventional system. Now, what we wanted to test was, extending the PSF seems to help. So what if we just defocus the system, right? In that case, we are defocusing it enough so we are not introducing nulls in the PSF, but we are reducing the MTF, right? So that helps the aliasing to some extent. So we see there's some benefit of doing that as opposed to a full PSF engineering. But when we do the PSF engineering combined with the subpixel shifting, we can get significant improvements, right? So in fact, here with just 4 by 4, basically 4 measurements, I'm actually beating the conventional performance, which may seem counterintuitive, right? How can you still have aliasing in the system and do better than optically limited system, right? And so we dug a little bit deeper into that, and basically what we are seeing is with the optical PSF engineering, you're shaping the MTF and enhancing the frequencies which are more important for discrimination. So you're selectively enhancing those frequencies, and that way you're tailoring the optical system to the algorithm sensitivity for detection, and you can get better performance. So we can actually get even better performance than the traditional system where there's no resolution limitation, at least detector resolution limitation. So hopefully this kind of shows you the power of using task-specific metrics, right? Depending on what you want to do with the image, that's how you should optimize the system. So this one is probably the most familiar. So I did some work on extend DOF, and one might think, this has been kind of solved problem, but we looked at, several papers in the literature, and now literally there are hundreds of them, between, Ed's first work in '95 and now. So this is the kind of system design we were pursuing. So we were interested in long-wave infrared imaging. So the system we had at hand was a focal length 25 millimeter system, F1 system, so it's really fast because you're photon limited at long-wave infrared, and the spectral window as long-wave suggests is between 8 and 14 microns. So this is like thermal imaging, looking at the heat emissions from black bodies. And in this case, basically because we want to maximize the depth of field, we put the system at the hyperfocal distance, in this case 25 meters. So it's in focus from infinity all the way up to the closest focus is hyperfocal distance over 2, so up to 12 meters, right? And the goal of this EDF design is that we want to pull the focus as close as possible, but the stated goal was 4 meters, right? And this, at that F number, is about 1.7 waves of defocus. Now, of course, the measurement SNR in long wave is not that great because we are using basically microbolometers, which are pretty noisy. And so at that noise level, the challenge is even more. And we are also specified a nominal SNR budget. Basically, the noise gain that we would incur as a result of doing EDF has to be less than 3 dB, right? So those were the specifications. So as we all know that, the cubic phase mask is definitely a solution in this problem space. It's separable, so its signal processing is simplified. You can do it with 2 one-dimensional filters. But it has low diagonal MTF, so in the reconstruction process, you can have artifacts as a result of kind of overshoot. There have been more, mature designs like the trefoil phase mask, and again, this is not intended to be exhaustive list of all the phase masks which are in the literature. We kind of picked the best ones that we could find, and we could reconstruct their performance by ourselves. So trefoil is another well-known design. This one is better, but it's not also provably optimal in terms of maximizing the volume of MTF in 3D space for a given SNR. So the objective for our design problem, and this is common with any EDF, is that we want to minimize the optical modulation loss in the MTF as a function of the engineering process. And then we also want to minimize the MTF variation process across the depth of focus because we want to apply only one filter, right, for all the depths. If the MTF varies, then we will get uncorrected kind of artifacts at different ranges. And we also want to minimize the MTF variation across the spatial frequencies, so basically in the full volume, right? So what we came up with is basically in terms of the phase mask parameterizations. Once again, we use Zernike phase mask. And one of the reasons for doing that was the Zernike polynomials can be also interpreted in terms of sidal aberrations. So we wanted to get some intuition in terms of what optical aberrations are actually useful for this EDF design process. So for example, if you look at the third order, you can see the 2 coma terms, the trefoil terms, and then you have 5th order coma. So we went all the way up to, I think, 9th order aberrations in this case. And we didn't use all the even orders because they basically are defocus terms. So we only use the odd orders. So for the objective function, basically we had a very simple objective function. So we want to minimize the system MTF, which is the optical times the signal processing MTF, the distance of that from a unit kind of MTF. So, or the optical cutoff or the optical bandwidth, what we want to end up with is a flat MTF. Now you might say that's not the ideal one. We should have kind of a diffraction limited MTF. And part of the reason we did that is that we wanted to emphasize that the error should be smaller at higher spatial frequencies. So if we put a triangular kind of MTF here, what we noticed at the higher spatial frequencies, as a result of the optimization, we are getting nulls. So this is somewhat artificial in order to counteract that and give higher frequencies more weight, because the power spectral density that we use in the Wiener filter, if it follows natural power law, then it has lower energy at higher spatial frequencies. So for the reconstruction, we use the linear optimal filter. So basically minimizing this MTF error. And the other thing you'll notice is this is the absolute value. It's not the mean square error. And this has certain advantages. And we basically integrate this error from the ideal one or the full focal volume. So in spatial frequencies and or the range of image distances that we are interested in extending the depth of field. So if you try to optimize this function, it's not convex. We resorted to simulated annealing kind of techniques. And we kind of converted our optimization process to a GPU-based process. So we literally, I think, went through 10 million designs to kind of come with a family of designs that were meeting our criteria of 3 dB noise gain. So this is basically the result of that optimization. Now, if you look at it visually, this looks very much like cubic phase mask. In fact, cubic and the trefoil. But if you do a decomposition, you will see there are significant components other than the cubic. So it has significant third order terms, which is the dominant cubic and trefoil parts, but it also has the fifth order and seventh order terms, which are significant. So what we did was we verified how much was of the improvement was a result of these higher order terms. So we basically set them to 0, and we get back a cubic phase mask, right, and a trefoil. And the noise gain in those resulting systems is much higher. So for a fair comparison, we basically use the same objective functions, and we parameterize the Zernike phase mask so that it's only in the cubic space, the trefoil space, and then this full dimensional space. And then we compare the result of those 3 designs. So this is simulation result at 24 dB measurement SNR. What I have is the star chart target. So you have different resolutions as you go to the center of the chart. And this is the hyperfocal distance. So this is the best focus of optics. This is 6 meters. So this is quarter of the hyperfocal distance. And this is the 4 meter, which is the target, right? So this is the conventional system. Now you can obviously see it is blurring. You can get basically the phase flipping as well when you have significant nulls. This is the cubic phase mask. We computed its noise gain to be 4.6 dB, so it was higher than the budget. And you can see also, because of the diagonal lower MTF, you can see some artifacts. As the Wiener filter is trying to push, you get, non-even, basically overshoot, undershoot, especially at 4 meters where it's trying to work really hard. This is the trefoil design. In the noise gain, it's slightly worse than cubic, but in terms of artifacts, it is a significant improvement. You can see in the first 2 designs. In the last one, the artifacts are much less, but there's still some contrast inversion happening at the higher resolution frequencies or high spatial frequencies. And this is the optimized phase mask. In this, we got a noise gain of 2.9 dB, so just below our specification. And you can see, I don't have the zoom in version, but we looked very carefully for image artifacts. This one, if you look very closely on the edge, there are slight artifacts. So it's not artifact free, but at least visually, at these spatial frequencies, it's much lower artifacts. And the noise gain is significantly lower. A dB can be significant noise improvement. So we went ahead and actually tested the system in lab. We acquired a couple of microbolometers cameras from Xenix, and they had commercial optics. We were lucky that the aperture stop was actually on the first surface, so all we had to do was fabricate a phase mask and use it like a filter. So we just slapped on the phase mask. So this is the EDF system, and this is the traditional system without the phase mask. And I think we used monocrystalline germanium. So we diamond cut the phase surface, and I think it was finished with MRF. So one thing I should mention in the phase mask, if you look carefully, there's almost no axis of symmetry. So this is a free-form surface, right? So you have to rely on basically full diamond turning process to fabricate that. The peak to valley variation, from what I recall, was about 1.7 microns. So at that wavelength is not much. So the fabrication challenge is not that great. We could make it easily with very high tolerances. So these are some results from the experiment. We basically constructed some bar charts out of polymer. We used a 3D printer. We could print any bar chart we wanted. And we designed that at different spatial frequencies. So going back, just to give you a sense of scale, the highest spatial frequency, which is limited by the detector, in this case is 20 lines per millimeter. Okay, so that's the Nyquist. And we printed this bar charts at, one was actually above Nyquist frequency, this one is just about. At 6 meters, you could say the conventional system is somewhat, resolving the bar charts. They're almost kind of on the edge, right? Whereas with the EDF system, with the Zernike, they are much clearly resolved. Of course, you can see some of the noise gain which is coming through, right, in this kind of speckle pattern. Then especially at 4 meters, the improvement is really obvious, right? So at close to cutoff, the conventional system can't resolve these at all, or even at lower spatial frequencies is losing modulation, whereas the EDF system clearly resolves them. So those were on test targets. We had some natural scenes. Basically, we put a Christmas light string with traditional bulbs because the LEDs don't have much of a heat signature. So these were kind of acting like point sources, so we could see how the blur is happening. And we string it from like 25 meters. This was a hallway in the college, all the way up to 2 meters. So you can see as they're getting closer, they're getting blurrier. And this is the EDF system. They stay sharp almost up to 2 meters. And then from 2 meters, you can see the PSF is uncorrected. So you see some of the triangular artifacts. So it works even actually down to 2 meters with some artifacts. So this is kind of a, you see, I think it's supposed to be a video, yeah, of one of my students walking through the hallway. So you can see really as he's getting closer, you can see the finer detail on his t-shirt there. See if we can stop in time. So you can really see here, the detail is very obvious, the improvement in the resolution. Okay, so kind of switching gears a little bit, going from point spread function engineering approach for computational imaging to compressive imaging. So this is kind of a subset of computational imaging systems that I have interest in, and I'll start with a basic motivation of why compressive imaging and what it's about. So here is a kind of a block diagram of a traditional imaging system. So the goal is that you're trying to get a picture of some object with high fidelity, say in the MSC sense or resolution, and then you design a very nicely or a very nice optical system with Nyquist match detector. You get this image measurement, of course, is corrupted by noise from the signal and the detector. But typically, first thing you do on a digital camera is you compress that picture, especially on DSLRs, right? Or almost on all cameras, including your cell phone cameras. And you can get about 10x compression without almost any loss of visual quality, at least for most of the people. Some people have very high acuity, you could tell. So what that tells you that if you can compress that image without loss of at least apparent resolution, then the image is redundant to start with, right? There are lower degrees of freedom than the number of pixels that you have measured that suggests. So you can, this one is showing you can decompress and get about the same measurement. So in that sense, if you think about it mathematically, natural objects or scenes are sparse or compressible in some sense, right? And evidence of that is that if you take, for example, this image and you do a DCT transform, most of the energy of the image lives in selected coefficients in the frequency space. There is energy, in fact, in almost all frequency components, but is negligibly small, right? So basically, compression, at least the simplest version of compression, basically throws away all the small coefficients, only maintains or digitizes this high energy coefficients, and that's how you get compression, right? So if this is true, then in a traditional optical system, we are acquiring this high density of data, and then we are throwing away most of the data, not necessarily information, right? So that suggests that we can use our system resources much more wisely if we acknowledge that we have prior information about the scene in terms of its smoothness and structure, right? So that's the key idea of compressive imaging. Now, instead of doing the compressive or compression post-measurement, we want to inject compression in the acquisition stage, right? So imagine somehow I could acquire the compressed image directly on my detector system, right? That has many benefits. It can reduce the number of detector counts. It obviously reduces data rate, and I don't have to post-process that image to compress it. It has multiplexing signal advantage if you are thermal noise limited. And also it can reduce the cost of a detector array, especially in long wave or mid wave infrared imaging, where high resolution detector arrays are really expensive, right? So that's the basic idea of compressive imaging. And the rationale for why it works is because signals are sparse. They are lower degrees of freedom than what Nyquist suggests, right? So in that kind of a system, if you do a linear modeling of such a system, P is the transformation matrix. P is going to be a what they call a fat matrix. It's going to be narrower than wider. In a traditional system, this matrix is square. It's almost isomorphic, right, for diffraction limited system. So mathematically, if you think about it, it's an ill-posed problem, and you can't solve it, right, without extra information. So that's exactly the prior information we use. We know the image is sparse in some domain, say wavelet domain, DCT domain, and we use that information to invert the object almost perfectly as limited by noise. And so that's the rationale of compressive imaging, or compressive sensing, as it's known in the mathematical community. So again, it hinges on this idea of signal priors, which is knowing that signals are sparse, but we can also kind of take the compressive imaging to the next step and introduce task priors, right? So which is also injecting the information what is it in the image that I'm looking for, right? For example, if I'm just looking for target, you could argue that there's only one bit of information in the image, right? All I care about is whether the target is present or not. I don't care about its orientation. I don't care about its brightness. I don't care about what clutter there is in. So there's many sources of entropy in the scene, but there's only one type of information I'm interested in, right? So that kind of information is captured by task priors. So depending on the task you have at hand, the information in the scene can change, right? So that's quite a thought-provoking idea, but that's just acknowledging the kind of definition of information with regard to what I care about, right? So to capture that task prior, basically, you can think of the task at hand induces a specific parameterization of a scene in terms of its sparsity and changes its inherent task-specific sparsity, right? So that's the task-specific prior. And as I mentioned, if we exploit both the signal prior, which is of sparsity, and the task prior, we can make the compressive imaging even better in the sense of compression ratio that we could get and improve the system performance and the size, weight, and power. So the question becomes, how do we actually do this? How do we exploit the signal and task prior information to design the measurements? Because as many of you know, in compressive sensing, at least the vast majority of the people are using random projections, which have theoretical performance guarantees. But they don't completely exploit all the prior information that you have available for natural scenes. So how do we incorporate that extra prior information in the measurement? And then how do we go to the next kind of the evolution of the random measurements? So that's the question. So, later on, I'll show you the formulation of this task-specific information, which kind of addresses how we fold in all this prior knowledge about the signal or the scene and the task into a joint framework and design optimized compressive measurements away from random and improve the performance as a result of that. So actually, that is what I'm going to talk about next. I thought it was later. So this is the notion of task-specific information. So here what I'm going to assert is that for the same scene, basically a scene with some clutter and a target, so this is a cartoon, the amount of information can vary. So in this scene, if I am only interested in detecting a target, whether it's present or not, then we can say the probability of absence or presence is half. Then at most the information content in this image is 1 bit, right, for that task. Now if I change my task, say I want to detect and also localize the target, say I want to localize it to one of these 4 quadrants, then what is the amount of information? Well, if we assume kind of equal priors, then I have half probability of it being present or absent, and when it's present, I have quarter probability of it being in any of these quadrants. So if you do the math, it's 2 bit of information, right? Same image, different information content, depending on what you care about. Now, if I want to do estimation task, which is just image formation, I just want to form a pretty picture of the image, then the information content changes again, because now it is important that I reconstruct not only the target, but also the background to as high a fidelity as possible. So there, the information content, and theoretically, from the information theoretic perspective, is given by the entropy in the scene, right? So, this is kind of a idea of how we might define task-specific information. Now, how do we mathematically define it, right, rigorously? So we do that by basically doing a parametric model of the world or scene. So we say that a scene is generated by this kind of a model where virtual source variable or set of variables basically parameterizes what I care about. So for example, in a target detection task, this X is a binary variable 0 and 1. It switches on and off, and it injects a target into the scene. And then that goes into a stochastic encoder, which generates the background, basically is a world model, generates the background. It might vary the target location, orientation, and so on, and that gives me this image, right? So I have a variable that I can address my task-specific information to. Now, these are some examples of a result of such a, at least in this maybe somewhat naive world model, you have tank present in different location, different clutters, and this is the target absent case. Your clutter can vary, but there's no target, right? So this introduction of source variable basically gives us a handle on how to define visual information. So again, back to kind of a block diagram of imaging system. This is the scene generation model. So given the source variable, it generates the real world scene for me, and then that goes through some imaging channel, is distorted, say by the optics, detector, and corrupted by noise, and this is my measurement, right? So now I can define the task-specific information formally as the mutual information between R, this is my measurement random variable, and X, this is the variable which parameterizes my task, right? So mutual information is an information-theoretic measure, as many of you know, between how much information is shared between two random variables or set of random variables, right? So the higher the mutual information between X and R, the more information I'm basically embedding into my measurement about my task, right? And of course, it's upper bounded by the information content of X. You can't get more information than what there is to start with, right? So I won't get into some of the mathematical details, but computing this mutual information and then optimizing with it is quite challenging. So we made some mathematical breakthroughs to be able to do that for imaging systems. So this slide basically talks about, okay, so well, I can quantify the task-specific information based on the task, but how does it relate to more traditional metrics? Okay, so there are known connections between mutual information theory and statistical theory. For example, for classification or detection problem, from the digital communication theory, we actually know that the mutual information creates or gives you an upper bound on probability of error of deciding whether some random variable is 0 or 1 or which class it is. So basically, by maximizing this the mutual information, I can minimize the probability of error indirectly, right? So there is a connection between the classical metric. Now, for estimation tasks, for example, if you're doing reconstruction, there's also another this result is not as well known, but the mutual information basically gives you a lower bound on the minimum mean square error that you can reconstruct a target with, right? So again, by maximizing the mutual information, you can reduce this bound on the minimum mean square error and then hope to improve the image quality as judged by MSE. So again, because of this virtual source parameterization, it gives us a handle of how to incorporate signal and task priors into our world model. So task priors are incorporated by basically a probability description of X, and signal priors are incorporated through the stochastic encoder model, which captures the correlations between different pixels in an image. So given this metric, we can exercise that to kind of design compressive measurements which improve the performance beyond the random projection design, which is kind of the de facto standard in the compressive sensing community. So before I talk about the optimization, there are broadly two classes of compressive imaging systems I'm going to talk about. One are called static designs, and the other are adaptive. So what I mean by static design is that given the scene and task prior information, I can compute my projection matrix or the compressive design ahead of the measurement, and I'm not going to change that during the measurement process, so it's static. Whereas in adaptive, as I'll talk about next, what you can do is you can use the prior information that you have at hand before designing the imaging system, but as you are making measurements, every realization of a scene is different from another one. So there is extra information embedded in the scene, so hopefully you can learn that information as you make measurements. So you're going to adapt your measurement as a result of what you're learning from the experiment. So that's the adaptive design. So in the static case, again, the compressive measurement matrix design is basically an M by N matrix, and the goal mathematically is to maximize the mutual information between G and the parameterization of the scene theta for reconstruction task or classification task, whichever it may be. And you have to obey the design constraints. So these design constraints can come from computational complexity and of course from the physics of the problem. And that part is pretty important, and it has been somewhat ignored, at least for the optical implementation of compressive imaging systems. So I'll talk about this a little bit, but in terms of optimization of PSI or this mutual information, basically we used a gradient-based optimization approach where we compute the gradient of the projection with respect to this mutual information metric and subject it to the physical constraints, and we make some approximations, and that gives us a handle on designing these projections. So on to the case of adaptive design, as I mentioned before, this is kind of a feedback loop. So what we do is we design our first projection or compressive measurement using the signal and task priors. And so that's the measurement part. But based on what we learn on G, right, through a Bayesian inference approach, basically the measurement on G informs my update on the prior of theta. So that's the posterior, right? So I have some prior, I make some measurement, I learn some more information about my object, I can basically update my prior model of the object and then use that to design my next measurement, right? So in this feedback loop, I learn and then I adapt and measure again. So I hope that I can improve the imaging performance as a result of this kind of learning process, right? So that's the adaptive design. Again, in adaptive design, we design one or a set of measurements at a time, as opposed to in static design, we design all the measurements, at a time. So again, we use a gradient-based optimization, and we use Bayesian inference to update the priors, and basically use a similar approach as the static case in terms of the design. Now, onto the measurement design constraints. As I mentioned, there are some physics-based constraints that we have to obey. We don't have an option of ignoring them. So, as you might be aware, in the vast majority of compressive sensing literature, the normalization that they use on the projection matrix is the L2 normalization. So basically they say the L2, or the energy, right, for each projection, and the sum of that through all the measurement is constant, right? And that's definitely a valid normalization if you are measuring fields directly. So for example, in RF systems, or in systems where you can actually measure fields directly, that's exactly the right model to use. And basically that tells you you have some conserved energy, measurement energy that you can use. But in optical systems, in most cases, we can't make direct field measurements, right? Our detectors are only responsible to intensity. So now I have to basically change my constraint and acknowledge that the projection matrix is directly operating on the optical power, right? So in that sense, the absolute value sum of this projection matrix has to be less than or equal to some energy constraint, right? So this is a very different constraint mathematically than what they use in compressive sensing. And anytime you see anybody using this constraint for optical imaging, that's physically unreal, right? Or at least is not conserving the energy that you are using in a measurement. So this is basically the photon count constraint, and the kind of constraint you have affects the design of the projection matrix significantly. So I won't have time to get into that, but if you look at the design of the projection matrix as a result of this TSI optimization, and you have the same prior information in both cases, when I design with photon count constraints, my measurements look very different than for the L2 norm case. In fact, when you have the minimal prior information, you can actually show information theoretically that head-mount matrices are optimal. They maximize your multiplexing advantage, and you actually get that result from the photon count constraint. So next I want to share some result of using the static and adaptive information optimal design framework, first for the task of image formation, and then to finish with, I'll talk about task of target detection. So again, before we can actually optimize the measurement, we have to define some kind of signal prior which captures the sparsity of natural images. And in this case, we use the wavelet domain to capture the sparsity. And this is kind of the statistical prior we used on the wavelet coefficient. So basically what we notice is that if you if you sample from the wavelet space, the distribution on a particular coefficient looks like this. It is very heavily concentrated around 0, which says that there's a high probability that it's just going to be 0 or close to 0. And then it has heavy tails, which says there's a smaller probability that it's going to be significant, right? And that's capturing this compressibility part of the natural scenes. So we basically formalized a signal prior distribution, in this case as a binomial Gaussian mixture distribution. So we have a mathematical description of the sparsity of the image, and we inject that into our information optimal design process. And these are some reconstruction results, hopefully conveying some of the improvements we get as a result of this task-specific measure. So here the compression ratio is set to 4x, it's somewhat modest, and the measurement noise is 1% of the dynamic range. So for example, in an 8-bit camera, 1% is about 2 pixels, standard deviation, which is, a decent SNR camera. So this is the object, some example objects. This is the reconstruction using random projections in the forward sensing matrix. And you can see it has significant artifacts. Even at 4x, it's struggling with noise. So many of the results you might actually see in compressive sensing papers, at least the initial ones, were done without noise. And of course, in reality, you have to contend with noise. And that's where the kind of devil in the detail is. The random projections are really sensitive to noise. And that's where we benefit from our information optimal design. So not only are we exploiting the additional prior information we have at hand, but we're also making the measurements more robust to noise. So at least in the optical domain, we are doing that by basically maximizing the photon efficiency of the measurements, not only the sparsity. So this is the case where we use the TSI, basically measurement design. This case is interesting. This case, the way you get compression is that you just bin 2 by 2 pixels. So this is equivalent to if you had kind of detector undersampling, right? If your detector was twice the Nyquist limit, you automatically get downsampling as a result of that compression, right? And then you can reconstruct that with different nonlinear reconstruction techniques. So it appears that just doing undersampling is actually even better than random projections. So you don't have to even change the optical system. You can do better than that. But if you incorporate that prior information, you can of course beat this and get this quality of images. So hopefully you can see these rails are much better resolved than either one of these cases. Now 4x is not that great a compression, and 1% is not that much noise. So what we did next was we upped the noise to 5%. This is pretty noisy. And you can see the other designs are sensitive to the noise much more than TSI. So random projection starts to basically break down completely. You see this kind of blocking artifacts because it's done block by block. Even the binned projection, which is basically undersampling, has noise deterioration, whereas in TSI, what happens is that when you go to the low measurement noise limit, your projection becomes close to binary, which maximizes the photon throughput at some cost of exploiting sparsity. But at low SNR, photon throughput is more important. So the design changes as a result of higher noise, whereas these measurement designs don't acknowledge noise and as a result suffer from that. Yes? Oh, so I didn't say that. So reconstruction technique is basically a minimum mean square error, and it's a nonlinear reconstruction technique. So from the MSE point, it's provably optimal. In terms of complexity, is much higher complexity than most of the CS algorithms you have. So there is some trade-off in the reconstruction. You pay the price of that, but you get better performance. So in this case, I maintain 1% measurement, but up the compression ratio. So even for the TSI case, there's more artifacts at higher compression ratio, as you can imagine, because you have smaller amount of information that you can capture, but it's much more robust to compression ratio degradation than random and binned one, right? Hopefully it's obvious from this set of examples. So these results have been all based on static measurement design, where I use the signal prior information and design and fix it. I don't change it during measurement, as opposed to adaptive design. So we have just recently finished a study on that, and we can see some significant improvements, at least at lower compression ratios. So again, this is the object, this is the random measurement, it's static, it's not changing. This is the static TSI, or information optimal measurement. So this is what I've been showing you, and this is the adaptive one. So you can see from random to static, as we incorporate more prior information and we capture the photon count constraint, we get improvement. But in adaptive case, we get further improvement as we learn from the actual signal at hand. And of course, in adaptive, you have to sense, adapt, and design the projection. So it has some real life consequences in terms of how fast you can adapt. And most of the algorithms right now, they are far from real time. But we are working on that to see how we can basically lose some optimality in their design, but be able to do the design in fraction of a second, basically at the frame rates required. So hopefully this shows you some benefits of the adaptive advantage in compressive sensing. So the last basically topic I want to talk about is compressive imaging, but for target detection case. So here my goal is very different. I don't want to make a pretty picture of the object, but I just want to detect a target of interest. And in this case, I'm only showing you static. We have some work on adaptive as well. So our target model, or the world model, is somewhat like this. It's somewhat naive. We basically have the target, in this case, a tank, and it can be at different locations in the scene. So I think in this case, we allow 80 different locations in the scene it can. So the location is kind of the nuisance variable. And then we have a mixture of different clutter components. So this generates the background clutter. This generates the target at one of the allowable n locations, and this gives you a general scene based on that model. So here the virtual source variable, again, just to remind you, is just going to be binary instead of wavelet coefficients as it was for the image formation task, and it's going to just take values 0 and 1. So all I have to do is detect that, right? So in this case, what we did was we are pursuing some information optimal designs, but in the meanwhile, what we did was we tested several kind of well-known designs from the literature. So what if we use a generalized match filter for the projection, or a Fisher discriminant, independent principal component analysis, and of course random projections? What if we use that in the measurement process as the compressive measurements, of course subject to photon count constraint? What would be the performances of these candidate kind of projections or compressive measurements? So just for sake of completeness, I'll quickly go through what generalized Fisher discriminants are. Basically, in a discrimination problem, if you're trying to resolve two probability density functions, class conditionals. So here I've just made a 3D example of this. In an image case, in a real world case, this can be million dimensional, right? You have million pixels. So you're trying to discriminate between these two, and if they're at least well separated Gaussian clusters, then you can define a linear discriminant which separates these two dimensions, right? So for a two-class problem, you can show that, or a detection problem, that there's only one discriminant surface, a linear surface, and so if you project your scene onto that projection, then you're done. You have all the information you need. But of course, in real cases, class conditional distributions are not Gaussian, so this is somewhat of an approximation. So for the generalized Fisher discriminant case, what we did was we made the target position also a variable of interest, at least in the terms of projection design. So from a one class or two class problem, whether target present or absent, we went to a 65 class problem. So the target is absent, that's one class, and then there are 64 classes when target is present. Which location is it in? That's also a discrete case, right? So and then we designed a 64-dimensional Fisher projection for that, right? It's the number of classes minus 1 is the dimensionality of the Fisher projection. And similarly, as many of you know, at least in the Gaussian case, the optimal filter for detection is matched filter. So we did a generalization of that matched filter as well. We got a projection matrix, which is shown here. So next, I'll show you evaluation of these different, basically projections or compressive measurements that we did for using TSI. So on this axis, the horizontal scale is SNR in linear scale. So 10 is just 10x, signal is 10 times, variance is 10 times higher than the noise variance. On the vertical case is task-specific information. Now I remember in this case, the virtual source variable is binary. So the most information you can have is 1 bit, right? So I can't ever get more than 1 bit of information. When I get 1 bit of information, I can do detection with 100% accuracy or 0 probability of error. Now, of course, when you have noise in the system, you can never do that with finite number of measurements. So this plot looks like it's getting very close, but it's asymptotic limit. So you can get very low probability of error, not ever 0. So here I have the performance of several systems. The dotted line is the conventional system. So here I'm not doing any compressive sensing. It's just a traditional, optical imaging system in which the optical resolution is matched to the detector. And as you can see, at low SNRs, because of the way it's spreading the few number of photons across a large number of detectors, you pay a huge price in terms of detectability. So you don't have a very good performance even with a traditional detector, which you might think is an optimal design, right? If I capture the whole image, then I have everything. Well, you might think that, but because of the noise, you're actually sacrificing the photons the way they're measured on the detector. The solid line is basically one version of the generalized Fisher projection. In this case, all we did was a two-class problem. We didn't acknowledge the position uncertainty, and as a result of that, it suffers. But of course, it's still better than a conventional system, especially at low SNRs. Now, of course, the other thing I should point to in fairness, with the conventional system, as the SNR increases, you can see it's getting up to the 1-bit limit, right? So it will ultimately perform as well as any other system, but especially at low SNR, you pay a heavy price of the suboptimal design. Now, this purple line is the generalized Fisher discriminant with the 64 positions, and you can see even at like 1:1 SNR, it gets about 0.8 bits of information, which is pretty amazing, right? So this is a result because you're exploiting all the information you know about the target and you're incorporating that into projection design. In this case, I think we made like 5 measurements as opposed to 6,400 measurements as a conventional system does. So all your photons are concentrated on only 4 measurements. Your SNR of the measurement is much higher, right? And it's tailored to the task that you want to answer. So this is just to quantify. We also tried PC projections and ICA projections just to kind of throw them in there, see how they perform. But of course, the Fisher discriminant projection is maybe somewhat the most targeted for this task. Because as you know, PCA and IC is not designed for target recognition. It's more for unmixing or reconstruction. So I think with that, I can probably conclude the talk. And I'll take questions instead of reading through the conclusions. Thank you.
We have time for one question. Or we can leave them for one-to-one. Okay, thank you so much,
Thanks again.
everybody, for coming.